would it be a good idea to share screen as we read through it?
That's true, yeah. Can we both share screen somehow? Because I noticed before that someone had to be host in order to share the screen. Can you share?
I seem to be able to share the screen from here as well, and I'm not the host. So I think anybody that's speaking can share the screen.
Okay.
Yes. For instance, I can try to share it just to showcase how it works. I'm using my phone though. Okay, host disabled attendee screen sharing. Oh, so I'm unable to share it because it has been disabled by the host.
It's disabled by the host. I wonder how I can enable it. Like,
okay, I can probably at the time you were setting up the meeting, or you can go back to the meeting setting. If you can find the link to the meeting, if you go to the settings, you should be able to find where you can adjust the settings. I'll also do a check after this meeting to maybe notify you of how you can go about it.
I can't find. I never saw. I will contact.
You may not be able to change that setting now. I'm not sure, but I'm saying if you go to the meeting setting on Zoom, if you log into Zoom and go to the meeting setting, you may be able to do that.
I don't. I will check back later to be sure, but like.
Maybe you do that later.
Yeah. Okay. So.
We can go ahead now.
Yeah, I will share screen.
Yeah.
The Road to Deep Learning, Chapter 1, Section 5. Much of this changed with the ready availability of large amounts of data due to the World Wide Web, the advent of companies serving hundreds of millions of users online, a dissemination of cheap, high-quality sensors, cheap data storage, Kreider's law, and cheap computation, Moore's law. In particular, in the form of graphical processing units originally engineered for computer gaming. Suddenly, algorithms and models that seemed computationally infeasible became relevant, and vice versa. This is best illustrated in Table 151. So they're showing how much progress was made with processing power and storage capacity. Yeah. Can you go ahead with the reading?
Okay, so you didn't hear me. I said reading from the table or the paragraph just after it?
In the next paragraph, it is evident that RAM.
Okay, so it is evident that RAM has not kept pace with the growth in data. At the same time, the increase in computational power has outpaced that of data available. This means that statistical models needed to become more memory efficient. This is typically achieved by adding nonlinearities, while simultaneously being able to spend more time on optimizing these parameters due to an increased compute budget. Consequently, the sweet spot in machine learning and statistics moved from generalized linear models and kernel methods to deep networks. This is also one of the reasons why many of the mainstays of deep learning, such as multilayer perceptrons, convolutional neural networks, long short-term memory, and Q-learning were essentially rediscovered in the past decade, after laying comparatively dormant for considerable time. The recent progress.
One question.
Okay.
Do you know what means kernel methods? Because it says
support vector machines.
Yeah.
Yeah.
What would be a good term to describe them? They're like even more expert systems than deep networks. Is that correct?
Okay,
Like
kernel
they're
method.
yeah, like they're even less intelligent, one could say. Like
Okay.
there's more manual labor required from the practitioner.
Okay.
Like feature engineering or so I was and yeah.
Okay.
Do you know why it's named kernel methods?
I don't know. I don't know.
No. Okay, let's I also don't know. I was just curious. Like, okay, let's just go ahead.
Okay. The recent progress in statistical models, applications, and algorithms has sometimes been likened to the Cambrian explosion, a moment of rapid progress in the evolution of species. Indeed, the state of the art is not just a mere consequence of available resources applied to decades-old algorithms. Note that the list below barely scratches the surface of the ideas that have helped researchers achieve tremendous progress over the past decade. Novel methods for capacity control, such as dropouts, have helped to mitigate the danger of overfitting. This was achieved by applying noise injection throughout the network, replacing weights by random variables for training purposes. Attention mechanisms solved the second problem that had plagued statistics for over a century: how to increase the memory and complexity of the system without increasing the number of learnable excuse me, please.
No problem.
Attention mechanisms solved the second problem that had plagued statistics for over a century: how to increase the memory and complexity of a system without increasing the number of learnable parameters. Found an elegant solution. Badenau et al. 2014 found an elegant solution by using what can only be viewed as a learnable pointer structure. Rather than having to remember an entire sentence, e.g. for machine translation in a fixed dimensional representation, all that needed to be stored was a pointer to the intermediate state of the translation process. This allowed for significantly increased accuracy for long sentences, since the model no longer needed to remember the entire sentence before commencing the generation of a new sentence. Multi-stage designs via the memory networks, MEMNET, and neural programmer interpreter allowed statistical modelers to describe iterative approaches to reasoning. These tools allow for an internal state of the deep network to be modified repeatedly, thus carrying out subsequent steps in a chain of reasoning similar to how a processor can modify for a computation. Okay, so I'm not quite clear about this multi-stage designs.
You're not quite clear about it, or?
Yes. So can I read it again, maybe?
Yeah, sure.
So multi-stage designs, e.g. via the memory networks, MEMNETs, and the neural programmer interpreter allow statistical modelers to describe iterative approaches to reasoning. These tools allow for an internal state of the deep network to be modified repeatedly, thus carrying out subsequent steps in a chain of reasoning, similar to how processor can modify memory for a computation. A little better. Another key development was the invention of GANs. Traditionally, statistical methods for density estimation and generative models focused on finding proper probability distributions and often approximate algorithms for sampling from them. As a result, these algorithms were largely limited by the lack of flexibility inherent in the statistical models. The crucial innovation in GANs was to replace the sampler by an arbitrary algorithm with differentiable parameters. These are often adjusted in such a way that the discriminator, effectively a two-sample test, cannot distinguish fake from real data. Through the ability to use arbitrary algorithms to generate data, it opened up density estimation to a wide variety of techniques. Examples of galloping zebras and fake celebrity faces are both testimony to this progress. Even amateur doodlers can produce photorealistic images based on just sketches that describe how the layout of a scene looks like. In many cases, a single GPU is insufficient to process large amounts of data available for training. Over the past decade, the ability to build parallel distributed training algorithms has improved significantly. One of the key challenges in designing scalable algorithms is that the workhouse of deep learning optimization, stochastic gradient descent, relies on relatively small mini batches of data to be processed. At the same time, small batches limits the efficiency of GPUs. Hence, training on 1024 GPUs with a mini batch size of say 32 images per batch amounts to an aggregate mini batch of 32,000 images. Recent work first by Lee and subsequently by Yu et al. And G et al. Pushed the size up to 64K observations, reducing time for ResNet 50 on ImageNet to less than 7 minutes for comparison. For comparison, initially training times were measured in order of days. So I'm skimming through it again, please.
Yeah. Like I also like I don't really understand it like from reading it once, you know. I think the real learning value comes from reading it repeatedly. Like
Exactly.
yeah.
So could we also make a slight change to the approach and maybe have anybody that reads it try to offer the explanation or the understanding of what they have read? Is that going to help?
Yeah, I mean that's yeah, like I wonder who should go first. Like, should the person who just read out loud start with that, or the person who listened?
Okay, it might be a good idea for the person who read it to start. It's not really bound to him. So if he struggles with explaining it, anybody can chip in based on their
Okay, yeah.
understanding. Since it's kind of a group discussion after all.
That's true, yeah.
And if you struggle, you can simply make it known that okay, you don't really understand it, and somebody else will try to.
Yeah.
Okay, so I should read it again.
Yeah.
So in many cases, a single GPU is insufficient to process a large amount of data available for training. Over the past decade, the ability to build parallel distributed training algorithms has improved significantly. One of the key challenges in designing scalable algorithms is that the workhouse of deep learning optimization. This is where the problem starts. One of the key challenges in designing scalable algorithms is that the workhorse of deep learning optimization, stochastic gradient descent, relies on relatively small mini batches of data to be processed. Okay, so what it's saying here is stochastic gradient descent relies on small mini batches of data to be processed. And that's what makes deep learning the force it is today. Okay, so at the same time, small batches limit the efficiency of GPUs. Hence, training on 1024 GPUs with a mini batch of, say, 32 images per batch amounts to an aggregate mini batch of 32,000 images. Okay, so on 1024 GPUs, 32 image per GPU, is that it? And a simple linear multiplication.
So push the size up to 64,000 observations. I'm not sure. First they said 32,000 images, and now they say 64,000 observations. Is it still?
Okay,
I think it's still. I think
okay.
Image and observation is can be it's the same. Yeah, it's synonymous here. I think it's really difficult to understand to understand what they're talking about just from reading this. Like, I don't think it's possible. But one question I was trying to ask you is the one sentence was that the stochastic gradient descent relies on a relatively small mini batches of data to be processed.
Yes.
Why does it rely on relatively small mini batches?
Okay, so I think my understanding of stochastic gradients descent is okay. So rather than computing gradient descent on all the data sets you have at once and taking a large jump in terms of, okay, we know during training of a deep neural network, we compute the gradient, and the gradient is used to, during the optimization step, is used to adjust the weights.
So
right?
just wait, just small adjustment steps, because otherwise it could be overfitting in any direction.
You could actually be missing the global minimum or the local minimum and simply be jumping around. So stochastic gradient descent ensures that when you train using small mini batches, with each mini batch you can update the weight of all the network at once. So if you have, say, for instance, you have 320 observations, you broke it down into 32 observations per batch, per mini batch. So with each mini batch, there's an update to the entire weight. So each mini batch is said to be a representation of the entire data set. So sufficient for you to be able to adjust the weight based on the gradients from that mini batch.
Okay. So small mini batch is like one way to
reduce overfitting.
Yeah, and to make sure that the delta is small, like for changing the weights.
Yes.
Yeah. Okay. Okay. I don't think we can understand the 32,000 images, and I don't think we can understand that right now.
Yeah, especially considering that it was said increasing the observations to 64,000 reduce the time to less than 7 minutes from initially order of days, from initial training times that were measured in order of days. So I see that difference to be so great that comparing it to 32K, 64K is just order of 2, right?
I'm not familiar with the correct way to describe that. Order of 2. Like my theoretical background is not very strong, so
okay. Okay. So what I'm saying though is, it was said initially based on training on 1,024 GPUs with 32 images per batch. So it led to an aggregate of 32,000 images. However, the recent development, they were able to take it up to 64,000 images or observations, which is just twice.
On the same amount of GPUs, or?
Yes, kind of on the same amount of GPUs.
Okay.
So which is just twice the number that was possible before. However, if you check the order of time, order of reduction in time, it's just too different. It's nothing comparable to the ×2, the twice, the twofold improvement in the number of mini batches or the number of observations.
Yeah, they also not. There's also not the mention of the size of the mini batch for the.
Exactly, there's not a mention of it. That's another thing.
Yeah.
So we don't know if it's truly, if it's 64 mini batches, for instance, or if they increase the number of GPUs or something else. Yeah, that's true.
That's. I mean, I looked at the references, but they're not directly linking to a PDF of the papers.
Okay.
But here there's a archive ID. We can have a look.
Okay.
Okay, it just doesn't work with just Googling it. Maybe it works when I. Oh, there's a leading one missing.
Okay.
Common way to speed up training of large convolutional networks is to add computational units. Training is then performed using data parallel synchronous stochastic gradient descent, with mini-batch divided between computational units. With an increase in the number of nodes, the batch size grows, but training with large batch size often results in the lower model accuracy. We argue that the current recipe for large batch training, linear learning rate scaling with warm-up, is not general enough and training might diverge. To overcome this optimization difficulties, we propose a new training algorithm based on the layer-wise adaptive rate scaling. Using LARS, we scaled AlexNet up to a batch size of 8,000 and ResNet 50 to a batch size of 32,000 without loss in accuracy. So this is from 2017. I think it's they're referencing also. Let me look. What about this one? This is from 2018. So maybe this is the one with the 64,000. Because this is only mentioning 32,000.
Okay.
But I'm thinking, what are you thinking? I'm thinking they're talking about increasing units, like making the stochastic gradient descent work with
64 mini batches.
Yeah, with more computational power, like not on the same not on the same hardware, like just making it work on bigger hardware. Yeah, because here originally they said 1024 GPUs, and then here they mention here it's recurring 1024 Tesla GPUs. I'm not sure what K and L is. Do you know what K and L is? K and L Intel. Okay, so seems to be a specific architecture from Intel. Knight's Landing, 14 nanometer mini-core microarchitecture. So a non-GPU approach. Oh, and then they're here at the last, they say 2048 GPUs. So maybe that's with the 64,000 is related to this example here. Okay, so should we wrap it up for now? And then there's a next meeting in 1.5 hours if you want to join that.
Yeah, that's fine then.
Yeah. I'm not sure myself if I want to upload this to YouTube, but in case I would argue for, would you agree or would you disagree if I would upload it to YouTube, the session we just recorded?
Hello there. Hello? Hello?
Yeah?
Can you hear me, please?
I hear you.
Yeah. So you were saying we should wrap it up, right?
Yeah.
Okay, that's okay.
Next meeting would be in 1.5 hours if you're interested in joining that.
I'll see if I can.
Yeah. And then I asked if you would be okay if I uploaded it to YouTube, or if you would.
Of course, I'll be okay with that.
Okay.
Yeah.
Okay. 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 See you soon. Bye bye.
All right. Thank you.
Thank you too.
Bye.
Bye.